Section 14.6, the equation of continuity. So first, some simplified assumptions. It turns out the motion of real fluids is complicated and purely understood. So turbulence, for instance, I once met someone who has gained their PhD from Stanford in turbulence, mechanical engineering PhD, studying turbulence. And that's because turbulence is where things get chaotic, where it becomes really unpredictable and wild. So here we're going to simplify things and just discuss the motion of an ideal fluid. We're not going to study it at the PhD level. To get a good foundation first. So an ideal fluid consists of these four ideas. First, an ideal fluid has steady flow. Another way to describe steady flow is laminar flow. That says the velocity of the moving fluid at any fixed point does not change with time. And this is something that's really wild to get to observe it. You can see it a little bit in the figure here, where on the left side, there is this steady laminar flow, where at any point within, as the fluid is passing, it's at a steady speed. But then on the right, it starts to disrupt and there's all these different speeds within until it becomes turbulent. But for an example of laminar flow, this video was posted about a year ago, and so there's like a water balloon type thing. And as holes are poked with a knife, the water comes out, and it looks like it's frozen in place like an icicle. But it turns out it's not. The water's still coming out. It's dumping out of the container it's in. It's just in this steady flow so that even when it's disrupted, you can see it's actually just water. It's just flowing so steadily that it looks stationary. So there's one example of laminar or steady flow. Some other ideal fluid characteristics. The second one is incompressible flow. So we'll take the ideal fluid density to be constant and uniform, that we can't compress our fluid or expand it. We don't have to worry about that. We can just say, hey, it has this one density, cool. Third, it's a non-viscous flow. So viscosity is roughly the resistance to flow. It's the fluid analog to friction. So you can imagine honey is very viscous. It's sticky, so it doesn't flow very quickly. We're going to here say that there's no resistive forces here. We don't have to worry about our fluid sticking to the sides. Finally, fourth, irrotational flow. So the fluid may flow in a circular path, but if we imagine a dust grain that's suspended in the fluid, it's not going to rotate about its center of mass. So we don't have to worry about it spinning or flipping. All right, so these are the basic ideas of an ideal fluid. And we're going to visualize the fluid flow by adding a tracer. So we can imagine there's fluid flowing around and then we just drop in some like food coloring, for instance, if it was water, so that you can see how that, what path it would take. And every bit of the tracer in this figure, right, where you can see the path that each of like the dyed things is taking, where it's going around this obstacle, it's in there, there's some sort of blockade. Each of these follows a streamline. So streamline tells you the path that a tiny element of the fluid follows, right? If you dropped in a little dust particle or a crumb, we'd know it would follow along one of these gray paths. Here's a way to draw the streamlines, right, where they're in the purple arrows, and the velocity will just be tangent to the streamlines, right? So at any point, the fluid element, you can get its velocity by just drawing the tangent line to the streamline. Now, because the velocity is tangent to the streamlines, we can't have streamlines cross each other, because if they crossed each other at that intersection point, there'd be two different velocities, right? Would it be the velocity along one or the velocity along the other? So our streamlines will never intersect, and we even see that here. They bend and they get close to each other, but they're not intersecting. Right, now the fluid speed is going to depend on the cross-sectional area. Because of incompressibility, the volume flow rate through any cross-section must be constant. And so from this, we can write the equation of continuity. And this is a really useful equation. It says the area at one instant times the velocity at that instant is equal to the cross-sectional area at another instant times the velocity or speed at that instant. And this is something you've probably observed before if you've used a hose that just has an open end, right? If you start watering your plants with a hose, what do you do if you want to get the water to go further away, right? Or to get more of a spray? Well, you can stick your thumb over it, right? And when you stick your thumb over it, all of a sudden the water starts being able to shoot much further and faster. Why? Well, because of this continuity equation. When you stick your thumb over the opening, you're reducing the cross-sectional area that the water can go through. So since the area is smaller, the speed's going to increase, and it's going to shoot faster and thus be able to go farther. So that's what's shown here, where when it's the wide open area, the water kind of dribbles out, but by sticking the thumb in there and blocking out some of the area to a smaller area, it now is traveling faster. So that's a nice conceptual example. Here's a depiction that shows the cross-sectional areas, right, where the area is wider here, so it's a smaller velocity, and then at the top there's a bottleneck. So the cross-sectional area is smaller here, and V2 is going to be bigger. And that's just because of the fact that the volume flow per second at both instants, 1 and 2, must match. So this will hold for any tube of flow whose boundaries consist of streamlines, which are going to be the ones that we consider, and fluid elements can't cross the streamlines. So they just have to get closer together or further apart. Right, we can rewrite the continuity equation as RV, which is the volume flow rate, is equal to cross-sectional area times velocity, and that has to be a constant, that it can only have a single value. RV is the volume passing a point per unit time. So we could also write RV as the total volume, where I'm doing a capital V here, it's a little hard to see, over the time. So we expect that the units here are going to be cubic meters per second. Now, if the fluid density is uniform, we can multiply by the density to get the mass flow rate, where we have density times the volume flow rate. So if we add in density, we know density is kilograms per meters cubed, so this gives us a mass flow rate units of the cubic meters will cancel, and we'll just have kilograms per second. In other words, the mass flow rate is looking at the mass per unit time. So those are some other handy calculations there. All right, let's look at a checkpoint. It says the figure shows a pipe and gives the volume flow rate in cubic centimeters per second and the direction of the flow for all but one section. For that section, what is A, the volume flow rate, and B, the direction of flow? So I'd like you to think this through, so go ahead and hit pause now. Okay. Did you hit pause? Did you come up with an answer? I'm going to trust yes. Well, we know that the volume flow rate has to balance out. And so what that means is that the amount that goes in will have to equal the amount going out. So we can take a look. How much is going in? 4, 8, 5, and another 4 are all going in. 1 going in. And then we can look at which ones happen to be going out. So 2 and 6 are the ones that are going out. So that adds up to 8 out. So for these to balance out, for there to be a steady flow, we need to make up the difference here. So the difference between these would give us, I believe, 13 and out, where I've just subtracted the 8 from the 21 to get the 13. Let's take a look. And it is 13 and out. So constant volume flow rate is the key here to get this continuity equation to work out. And that pulls us through the equation of continuity, which just as a synopsis, remember, area times velocity, that quantity has to be constant. And this is the fastest way to figure out how fast you're going. So you want to keep the equation of continuity quick on your tool belt so that you're ready to draw it out anytime you need to figure out how fast your fluid is moving.